Section 5-3 here is on the formal definition of antiderivative and indefinite integrals. The objective of this section is to evaluate antiderivatives and indefinite integrals using the formal notation. All right, so there's a proof here that we want to look at. And it's the proof of this constant times a function property. And if you recall, we talked about this in the first half of this section, that the rule for the indefinite integral of a constant times a function, the integral of k times f of x dx, turns out that's equal to k times the indefinite integral of f of x. So in other words, we can say that the integral of a constant times a function is the constant times the integral of the function. All right, so let's see if we can go through and prove why this is the case. And some of the problems that you're going to do are actually going to ask you to do some similar type proof here. So it'll follow steps very similar to the steps that we're going to go through. So let's define g of x here for us, just so that we can easily refer to one side or the other of this equation and use the definition of an indefinite integral, which is really what this thing relies on. So let's say that g of x is actually equal to the right side, the k times the integral of f of x dx, the right side of this property. All right, so then let's take the derivative of both sides here. Let's just take the derivative with respect to x of g of x, which is equal to k times the integral of f of x dx. And take the derivative of that whole thing with respect to x. So over here on the left side, we get derivative of g of x, of course, is g prime of x. And over on the right side, you have the derivative of a constant times the integral of f of x. Now, the integral of f of x is just some function. So this is really a constant times the integral of some, or excuse me, a constant times some function. And so I know the rule for the derivative of a constant times a function is the constant times the derivative of this function, the integral of f of x dx. So we're going to use a property that we know from derivatives over there. I can rewrite the derivative of this whole thing on the right as the constant times the derivative of my function. And if you look closely at what I have there, the derivative of the antiderivative of f of x, if you go back to your definition, the formal definition there of an indefinite integral, it turns out that if you take a function, find its antiderivative, and then follow that up by finding the derivative of that, you basically end up with the same thing you started with. So in other words, g prime of x is equal to k times f of x, is what we have over here on the right. And then finally, if you go back to your definition, your formal definition of an indefinite integral, if we say that g prime of x is equal to some function, and the function in this case is k times f of x, that's only true if g of x is equal to the antiderivative of this function, k times f of x dx. And there we go. That's our proof actually right there. I started out by saying g of x up here was equal to the right side of my property. And it turns out at the end that g of x is equal to the left side of that property. So g of x is equal to both of those, so therefore those two must be equal to each other. And like I said, the proof that you're going to see in your assignment there is going to be very similar to that one. All right, take a look at the differential here. Remember the differential, when we work with it, what we saw in the last section actually, is the differential is really indicating for us that the differences there in our x's and our y's. In the case of dx, it represents a small change in x. In the case of dy, it's a small change in y on our derivative. And the purpose of the differential in your problem is that it indicates for you your independent variable. So in the cases of dx, then that means x is our independent variable. If it's dt, then t is your independent variable, and so forth. In fact, the way that we read this indefinite integral here, if we say the indefinite integral of f of x dx, the way that's actually read is it's the indefinite integral of f of x with respect to x. So the dx part here, we read as with respect to x. In other words, it's saying with respect to our independent variable of x. That's what the dx actually represents there for us. So let's take a look at a couple of examples here then. If we take the integral of cosine of x dx, that's equal to the sine of x plus c. The antiderivative of cosine, of course, is sine. And notice that our answer is in terms of x. If I take the antiderivative of the cosine of t dt with respect to t, then I get sine of t plus c. The variable that you begin with and the variable that you end with are extremely important here. They're the same variable. Try one more of those. If I take the integral of cosine of u du, then I end up with the sine of u plus c. Again, notice that you end up with the same variable there in your problem. Okay? So the variable there, or excuse me, the differential there tells you your independent variable that's in your problem. Now, these ones here, I think it's pretty obvious that the fact that you started out with the cosine of u, you know what the variable is. However, let me give you one more example here. Let's say that we were trying to integrate just 5 dx. So if you look at your function here, the function is just a constant function. It's just 5. Y equals 5. We don't have a variable in there. Now you can see the importance of that differential. The differential is telling me what variable I should end up with. I have a 5 dx, so my independent variable is the x. Well, the antiderivative of a constant there is a constant times my variable, which I know is x in this case. And then, of course, plus my constant of integration, the plus c. All right? Versus if I had a problem like this, maybe it's 5 dt. Now, in this case, I know that the answer is going to be 5 times my independent variable. In this case, is t plus c. So you can start to see the importance of that differential there, especially on some of these problems where you don't even have a variable listed as part of your function because it's just a constant function. But it really indicates for you the independent variable. Okay, and you'll see that in your problems there that they're going to give you different variables as you do them, just so you get used to seeing different variables used in your antiderivative problems. All right, and that's the end of this section here for us.